In the previous lecture we considered the linear operators. Today we will consider a special type of linear operators called linear functionals. So let us start with the linear space and consider a mapping from this linear space into the field of scalars. Let's go with the general field of scalars, although for f we either take real numbers or complex numbers. So this mapping is called a linear functional. If it is linear. If it is linear for any scalars alpha and beta and for any elements of x, x and y. Well, as you can see, linear functionals are nothing but, well, they are the special type of linear operators. They are the linear operators with the codomain being the space, the field of scalars. So, no. Every linear functional is a linear operator. For a linear functional, we can define the notion of boundedness, continuity. As for linear operators, these two notions coincide for linear functionals. And for a bounded linear functional, we can define a norm, and so on. So we can do all the analysis we have done for linear operators, we can repeat it for linear functionals. One very interesting property. Denote by x star the space of all bounded linear operators on x, of all bounded linear functionals. So in the lectures about linear operators, we had a special notation for the set of all bounded linear functionals from one space to another. So in that terms, x star is L of x to the set of scalars. This space of all bounded linear functionals on a linear space, so x star, is called the dual space. And now let us state a proposition. The space x star is a Banach space. Why is it so? For bounded linear operators, we proved that the space of all bounded linear operators from space E to space F is Banach is complete if the codomain is complete. But in our case, the codomain is either the set of real numbers or the set of complex numbers, which is complete. Well, let us consider several examples of bounded linear functionals. For the first example, let us consider the space of all continuous functions. Let us define a functional f of x as an integral from a to b of the function x? Well, first of all, every continuous function is integrable, so this functional is well defined. By the property of the integral, this functional is a linear functional. And well, it is bounded with the norm of f equals to b minus a. On this space we can consider a more general function. So also for every continuous function y from this space, we can consider the functional f sub y of x, which equals to an integral of x of s multiplied by y of s. This is also a bounded linear functional. So we also have the f of y belongs to CAB, and then we take the dual, the asterisk. Let us consider the space of sequences summable with the pth power. On LP, consider a functional f of x equals to xi times yi, the infinite sum, for y being in LQ with 1 over q plus 1 over p being equal to 1. So we have seen this kind of relation between two parameters p and q in Hilbert inequality, and in fact to prove that this functional is well defined, by which I mean that this series converges, we need to use the Hilbert inequality. By definition, it is easy to see that it is linear and it is bounded. Let us know that the norm of f equals to the norm of y in LQ. That will be an exercise for you to prove. Let us now discuss several properties of linear functionals. Let f, which is not identically 0, be a linear functional on a linear space X. Then we have first, the codimension of the kernel is 1. Second, if g is a linear functional on X as well, such that kernel of f equals to kernel of g, then these two functionals are scalar multiples of each other. Scalar f, a scalar lambda, such that f of x equals to lambda times g of x for every x from x. And the third property, for every subspace of X, there exists a linear functional such that the kernel of linear functional f such that the kernel of f equals to this subspace first. So we want to prove that codimension of the kernel is 1. So let us first, since we initially assume that f is not identically 0, then there exists at least one point where f is non-zero. Let's take a point where the functional is non-zero. And let us consider another point, x naught, which is x prime over f of x prime. This element is also in X, since X is a linear space. And for this element we have the value of the functional equals to 1, since f is a linear functional. For every x in X, an element x minus f of x times x naught belongs to the kernel of f. In other words, every element x from X can be written in the form x equals to y minus f of x minus f of x times x naught, where y is in the kernel. And moreover, for every x, the element y and the first and the second element are determined uniquely, because this element depend on the fixed x naught and the value of f at the point x, so defined by x, so unique, and y is defined by this formula, so it's again unique for every x. So we have proven that any element of our vector space, linear space, can be written as a difference of two elements from two other vector subspaces, which means that we've written the big X as a direct sum of the kernel of f and the one-dimensional space span of x naught, of course plus. Yeah. And let us now recall how we define the codimension. The codimension of, well, in our case, the kernel of f is defined as the dimension of a factor space. But we have this direct sum, so when we consider the factor of x over the kernel, it is nothing but the second sum map, so it's a span of x naught. but the span of a single element has dimension 1. Let us go for the second part of the proof. So we have just proved that any element of our linear space can be written as a sum of an element from the kernel of F and a scalar multiple of any fixed x naught. Take x from x and write x as y plus f of x times x naught for some fixed x naught. In the second part of this statement we have the other linear functional g. Let us now apply g to this identity. By linearity of g. Also, we assume that the kernel of f equals to the kernel of g. And from the first part, we know that in this decomposition, y belongs to the kernel of f. So g of y is 0 then, because the kernel of f and kernel of y coincide. So it equals to g of x naught times f of x. And we have this identity for every single x in our space. Let us note that g of x naught cannot be equal 0, because otherwise g is identically 0, so it's 0 at every point, but the kernel of f and kernel of g coincide, so f is then 0 everywhere, which is not the case by our assumption. We take lambda to be 1 over g over x naught, and we're done. Let's prove the third part, and before we prove the third part, I have to correct the statement of the third part. So what is missing from this statement? So it's not for every subspace. We need an additional assumption on the codimension of this space Y. Because we claim that kernel equals to this subspace, but we have just proved that the kernel is of codimension 1. So this space is also has to be of codimension 1. For every subspace such that codimension of Y is 1, and then this statement is correct. So since codimension of Y is 1, well, by definition it means that the dimension of x over y is 1. Or this means that x factor y is a span of let's go for some y, let's go for x naught. Yeah, for some x naught in x such that x naught is not 0. In other words, for every x from x there are an element y from y and a scalar lambda such that x equals to y plus lambda x naught, and this representation is unique. And what is left to do is to set f of x to be lambda in this representation. from this definition, it is straightforward that f of x equals to 0, or rather f of y equals to 0 if and only if y belongs to the capital Y. Which means that y, the subspace y, is the kernel of f. The linearity of f is straightforward from the definition. Let us now move our attention from the general linear spaces to an inner product space, or rather to Hilbert space. Well, on the inner product space we have the inner product, which is a function of two variables, and we know that it is linear in the first component. So can we make a linear functional somehow out of the inner product space? Let us fix an element y from H and consider f of x on a Hilbert space from, well, let's go for complex numbers, given by f of x equals to the inner product of x and y. But y is fixed. Well, from the properties of the inner product, this functional is linear. Is it bounded? Let us consider the absolute value of f of x, which equals to the absolute value of the inner product of x and y. Let us now use the Cauchy-Schwarz inequality. We estimate this as the inner product of x and x raised to the power 1/1/2, and the inner product of y and y raised to the power half. What can we say about the first term? What is it? Norm of x. And the second one is the norm of y. So, the absolute value of f of x is less than or equal to, oh well, that's already written. The norm of f is less than or equal to the norm of y. Since f of y over the norm of y equals to the inner product of y over y and y equals to the norm of y over the y and y, so it is the norm of y. So the norm of f equals to the norm of y. So summing up, if we define on an inner product space, if we define a linear functional in terms of the inner product, then we obtain a bounded linear functional. Well, this is interesting, but I wouldn't say that it is surprising. So the surprising fact about this one, that any functional on a Hilbert space is of this form. And now we will prove it. Theorem. The theorem has its own name. It is the Riesz representation. Let H be a Hilbert space. For every bounded linear functional on H, or f from H star, there exists an element y sub f. I will write sub f, meaning that it depends on f. There exists an element y from H such that f of x equals to an inner product of f and y of f for every x from H. We have just proved that the kernel of a linear functional, not necessarily even bounded, the kernel of a linear functional is has codimension 1. Then H can be written as kernel of f direct sum span of x naught for some x naught in H such that let's rather go for yf. Such that y of f at this element y is not 0. Let us now take this yf and define a linear functional. A linear functional g by setting g of x to be x, y, f. What is the kernel of this functional? So we want, by definition of the kernel, all x's from H such that g of x is 0. I was a bit too quick writing y sub f here. Let's go for y0, just y0. It's close to the y sub f which we're looking for, but it's not it. So let's just go for y0. And y0 over there. Sorry about this. So we're changing yf to y sub 0. By the definition of G, the kernel consists of all x's such that x in a product with y0 is 0. So, in other words, it consists of all x's from H such that x is orthogonal to y0, or by linearity x is orthogonal to the span of y0 by linearity, which is by definition the orthogonal complement of the span of y0. But we have this representation of H as a direct sum of span of y0 and the kernel. So what is then the orthogonal complement of this? So that's the second segment in this sum. So it's kernel. And the very last step left. So what we have just showed that the kernel of G equals to the kernel of F, which is, by the simple proposition which we proved before, means that F and G are scalar multiples of each other. G equals to lambda F for some scalar. Well, scalars are complex now. Or f of x equals to 1 over lambda x y0 by the definition of G. Lambda is not 0 as we discussed previously, otherwise both G and F will be 0 functionals, or F equals to y0 over lambda bar. And that will be exactly the y sub f which we're looking for. Taking in a way similar to the one we used before, we can show that the norm of f equals to the norm of y sub f. So let us now prove uniqueness. As usual, to prove the uniqueness, suppose that there is y prime such that from H such that f of x equals to x y prime for every x from H. Hence, 0 equals to f of x minus f of x equals to x, the inner product of x and y sub f minus the inner product of x and y prime, or by linearity, by the properties of the inner product, which is true for every x from H. So this element, the inner product of this element with any element from H equals to 0, which means that yf minus y prime is orthogonal to any element from H, or equivalently yf minus y prime belongs to the orthogonal complement of H. But what is the orthogonal complement of H? 0. The orthogonal complement of the whole space is just the 0 element. Well, which means that yf equals to y prime, and we prove the uniqueness. This result is not very difficult to prove, although it's fairly interesting. It proves that any linear functional on a Hilbert space is generated by the inner product. But it has even stronger consequences. So in this Riesz representation theorem, we have constructed a one-to-one correspondence between bounded linear functionals on the Hilbert space and elements of the Hilbert space. And moreover, we have proved that it's not just one-to-one correspondence, but this correspondence preserves the norms. So moreover, it is isometric. Putting it all together, we have proved that there is a isometric isomorphism between the space H star and H. Thus, spaces H star and H are isometrically isomorphic. Isometrically isomorphic. And in the previous lectures, we have agreed that if the spaces are isometrically isomorphic, we do not distinguish them. We think about them as exactly the same thing. What we proved is that a Hilbert space and its dual space are exactly the same.